Hi, this is David. I am a research fellow with the Division of Mathematics Sciences. I will be your tutor in today's tutorial. So before we move forward to the problem-solving session, let us briefly review what we learned in the lecture. In the lecture we actually learned three things. The first, we learned the basic type of numbers. We learned the natural numbers, that is 0, 1, 2, on and on, should be a natural number. And we learned the integers, that is on and on, -2, -1, 0, 1, 2, on and on, and should be in the Z. And we also learned the rational numbers. So rational numbers actually, you can rewrite them as a fraction, m over n, with m and n be the integers. And usually they don't have a common factors. And we also learned the irrational number. Actually, we usually use the capital K to represent the rational numbers. So for the irrational numbers, however, we cannot write them as a fraction with m over n. But this is the numbers on this axis. And if we put rational numbers and irrational numbers together, we got the real numbers. And the second thing we learned is that we know how to do the Euclidean division. That is, suppose m divided by n, we got the quotient q and the remainder r. That is the same way of saying m equals to n times q plus r. And r must be smaller than n. Okay, with this definition of Euclidean division, we can further define what we call the modular congruence. That is, under the operation of mod n, a and b are equal. That is the same way of saying a can be written as b times k plus k times n for some integer k. The third thing we learn is the operator closure. That is, I give you a set. I give a set S. I give you an operator data. So the closure says if I have an element from S, another element from S, then under this operation S delta y, so after this operation we got another element, and this element still resides in S. So that's what we call closure. Okay, that's all for the recap. Now let's move to the problems. Okay, Q1 says 2 is the only prime number which is even. So of course we know it is true, and now we need to prove it. So we can prove by contradiction. So we assume 2 is not the only prime which is even. So that means we have at least one more even number, but it is still a prime. So let's assume this special thing, we call it 2k, all right? And k can be, I don't know, we don't know what it is, but it cannot be 1, right? Because if it is 1, then 2k is 2. It's not what we want, so it could be 2, could be 3, 4, and on. And then it must be some k inside this range. So now we have 2k. And for 2k, we know that 1 must be its divisor, and k must be its divisor, and 2k must be its divisor. So for these things, actually we have at least 3 divisors, right? And the key thing is that they cannot be equal, right? Because k cannot be 1, and 2k cannot be k. So we have 3 distinct divisors. That's contradict that this 2k is a prime. So we find the contradiction. Okay, for the second question, and show that if n squared is even, then n is even. Okay, let's do the proof using the contradiction. Okay. And suppose that n is odd. Okay, so n can be written as 2k plus 1 for some k, for some integers k. Okay, and we now know n squared. We know n squared is even, and n is 2k, so we know n squared must be 2k plus 1 square, and then we do the calculation. We find it is 4k squared plus 4k plus 1, right? And we put the divisor 2 together, and we can rewrite this as 2 times something plus 1. So what is it? It is an odd number, right? However, we assume that n squared must be even. So this is our contradiction. So n must be even. N cannot be odd. Okay, let's move to Q3. We need to show that the square root of 2 is irrational. Okay, so by the definition, we know if square root of 2 is irrational, that means it cannot be written as a fraction. So we still use the proof by contradiction. And we assume that square root can be written as a fraction m over n, with n an integer. Okay, then we do the following. We square both sides. We get 2 times m squared over n squared. So that is, we have m squared equals 2n squared. So that means m must be even, right? Because we have 2 here, so it must be even. And now we know m is even, so we can assume m is 2k for some k. And we put m to here, replace m with 2 times k. And what we have is, we can use this expression as 4k squared equals to n squared. And we simplify this. We have we have 2k squared equals n squared. Okay, so we have 2 here, so that means n squared must be even, right? And from the question 2, we know that if n squared is even, n is even. This is our conclusion. And okay, so what do we have now? So we actually have 2 things. First, we know m is even. Second, we know n is even. So, but we assume square root 2 is m over n. So they have a common divisor, right? So because m is even, n is even, so they have a common divisor too. This is a contradiction. We assume that they do not have a common divisor. Then this proves that square root of 2 is indeed irrational. Okay, now let's move to question 4. Okay. Okay, Q4. Q4 is simple. It has 2 sub-problems. First, I need to improve A mod n plus B mod n is congruent to A plus B mod n. So this says, so where you put modulo, n is not important. You can put modulo n right after A and B, or you can do the addition first, then you do the modulo. So whatever you do the addition first or you modulo first, the result is the same. So how do we prove this? We can do like this. And we assume that A mod n is some number, right? We just call it A prime. And we call B mod n is another integer, B prime. And we, from the definition, we know that, so by definition, we know A prime must be Q n times A. And B prime must be R n times B. And we put A prime times B prime as Qn times A plus Rn times B. And we put this term together. We have Q times R n times A times B. So if we do the modular, that is mod n, so this thing becomes 0. So we immediately have A times B. So this thing is what we want. Okay, we are done. Okay, the second subproblem is I need to prove A mod n times B mod n is A times B then mod n. Actually, we're using the same technique. We have A prime here, we have B prime here, so we can do the left hand side as A squared is Qn times A times B prime is Rn times B. Then we do the calculation, we find the result is Qrn squared. Same thing, and we have Q B n times A R n times A B. And so what's this thing? It is, so now we're doing a modular n. So this thing is 0. It is 0. It's 0 because we have n here, a factor n, and the remaining part is A times B. It's exactly what we want. So this is what we want. Finish. Now let's move to Q5. And Q5 asks to compute the addition table and a multiplication table. By the integer 0, 1, 2, 3. So we draw a table. So addition, we can draw the table as the following: 2, 3, 0, 1, 2, 3. Then we'll fill the blank 3 and 1, 2, 3, 0. Remember, this must be modular 4. and this give me 2, 3, 0, 1, and 3, 0, 1, 2. And likewise, we can do the multiplication. So we draw another table. Then I fill the form, so I don't repeat the procedure here. Now let's talk about Q6. And Q6 asks you to prove P times P plus 1 over 2 is congruent to 0 under the operation of modular P. And P is an odd prime. Okay, let's prove it. We know P is odd. That is, P plus 1 is even, right? And if P plus 1 is even, P plus 1 over 2 must be an integer. Let's call it, give it a name, Q. And now the expression becomes P plus 1 over 2 as now we have Q here, so we have Q times P, right? And this is the same. That's Q. So if we do the modular P, it must be 0. So this completes the proof. Now let's talk about the last question. And the last question has 4 sub-questions for the first one. So if S is the set of all integers, and I define the operator as the multiplication. And is S closed on the third? We need to see the result. We can define X in S and Y in S. And because S is an odd integer, so X can be written as 2P plus 1. And Y can be written as 2Q plus 1. Then we do the operation as the multiplication. So that is, we put our 2P plus 1, we put 2Q plus 1 here, and we have 4PQ plus 2P plus 2Q plus 1. And we find the common factor to here, so we put outside as P2PQ plus 2 plus P plus Q plus 1. What is this? It is an odd number, so it is indeed closed. Okay, now the second problem is let S be a it's a non-zero rational number R, but excludes 0, and the operator is division, so it's as closed on the division. So we can solve the question as we have x. It's a rational number, so it can be written as m over n for two integers. Must be s, and the y is another pair of integers as m prime over m prime, and we do the division, x divided by y as n. So this is actually times n prime m prime. So this gives me another fraction. So it must be a real number. So it is indeed closed. And for the third question, this time S, it's a set of natural number n, and our operator is subtraction. So it's S closed. Now we have so this is actually, the answer is actually no, and we now need to argue this by finding a counter example. So here I can say x is 5, okay, it is a natural number, and we find y is a natural number, let's call it 10, and x minus y is minus 5, but this thing is not a natural number, so it's not closed. Okay, let's talk about the last sub question. And this time S is the set of irrational number. I, and the delta this time is the addition. So it's as close this time. The answer is no, it's not closed. We can easily find a counterexample. Say square root of 2 is in I, and minus square root of 2 is I. However, 2 plus minus 2 is 0. This thing is definitely not an irrational number. Okay, this is the example, and an interesting thing I want to mention is that we are using the fact that minus square root of 2 is irrational number, but indeed we need to prove this, and we need to prove we put the symbol here. Minus is still a irrational number, and we can prove this by contradiction. That is, we assume minus square root of 2 is not a irrational number. It is a rational number. So that is minus square root of 2 must be a fraction m over n for 2 integers. And from the previous problem solving, we know that square root of 2 is indeed irrational, right? And from this thing, we put minus to the right hand side. We have square root of 2 is minus m over n, and we can put minus here. So this is again a fraction, because minus m and n must be an integer, and this thing is the same way. It must be irrational number. However, we have concluded that square root 2 cannot be rational. It must be irrational. So this is a contradiction. That is saying minus square root of 2 is irrational as well. Okay, so that's all for today's tutorial. I hope I have presented the solutions clearly to you guys. Have a nice day.